Alright, our goal in this video is to graph this function. Let's start off by finding the x and y intercepts, okay? Well, to solve the x-intercept, you want to solve the equation f of x equals 0, which is the same thing as 3x to the 4 minus 6x squared equals 0. And then why don't we factor this? So we have a common factor of 3x squared. So it'll be x squared minus 2. And if the product of two things is 0, that means either the first factor is 0 or the second factor is 0. So either this is 0 or this is 0. We basically solve each of these individually now. If I divide both sides by 3, I get x squared equals 0. And then I take the square root of both sides, and I get x equals 0. So that's one x-intercept. Over here, I get x squared equals 2. And, technically speaking, there is a plus or minus in front of here. But plus or minus 0 is just 0. But over here, it really matters, because when I write it over here, I get x is plus or minus the root of 2. So I hope that was clear. I'm just saying whenever you do the root of both sides, you should really put a plus or minus in front. Let me just write that a little bit better. But the thing is, so this is what we had, right? And then we hit both sides with the square root. And I'm just saying there should be a plus or minus in front of that. And since plus or minus 0 is just the same thing as 0, over here we just get one answer, but over here we actually have two answers. So the x-intercepts are, this is our conclusion, it's 0, 0, and root 2 comma 0, and negative root 2 comma 0. Now the y-intercepts, do those over here. The y-intercept is always easy because we just do f of 0, right? So 3 times 0 to the 4 minus 6 times 0 squared, that's just 0, right? So the y-intercept is 0, comma 0. So if you can, whenever you do a graph in calculus, if you can find the intercepts, it's always worth doing that. So let's go on to the main stuff of what we got to do here. 1 second. So let me repair this here. Okay. Excuse me. There we go. So let's recall that our function is 3x to the 4 minus 6x squared. What is the derivative of that? Well, it's 12x cubed minus 12x. And what's the second derivative? 3 times 12, 36x squared, minus 12 times 1 is just 12. Now what I'm going to do is this. I'm going to make a little chart here. I'm basically just going to divide my paper in half, okay? Over here I'm going to work with the first derivative. I'll just recopy it. And over here I'm going to work with the second derivative. And the reason I write these beside each other is because whatever I do on one side, on the other side, it's going to be exactly the same process, okay? Let's factor this. If I put all to 12x, I get x squared minus 1, right? And x squared minus 1, you can write as x minus 1 times x plus 1. And let's solve for the critical numbers now. The critical numbers is where the derivative is undefined or 0. You know, this derivative here is always defined. So the only kind of critical numbers here is where the derivative is 0. So let's see where that's 0. So 12x times x minus 1 times x plus 1 is 0. And we just set basically each factor equal to 0, right? If this is 0, that means x is 0. If this one is 0, that means x is 1. If this is 0, that means x is negative 1. And those are the x values of our critical numbers. Let's keep going. Let's also find the y values, okay? It's always good to do that. But I'm going to be putting this, now how do I find the y values? Do I put in the derivative or in the original function? Well, of course it's going to be in the original function, because when I put these three numbers in the derivative, I get 0, right? I'm actually interested in the y values for the original function. So when I put 0 in the original function, I get my y value to be 0. When I put in 1, I get 3 minus 6, which is negative 3. When I put in negative 1, I also get 3 minus 6, which is negative 3. All right, let's do a little chart here to figure out what's going on. Our critical numbers, we got 0, negative 1, and 1. And our derivative, let's think about the sign of our derivative here. If we take any number around here, like maybe negative 2, and I put it in there, I have negative times negative times negative. So that's a negative. If I take any number around here and put it in, such as negative 1/2, it's going to become positive, because this will be negative, this will be negative, but this will be positive. And if you think about it, any number in this region will make the derivative negative, and any number over here will make it positive. So you see, the negative signs on the derivative mean the function's decreasing, and the positive mean it's increasing. So we can answer some questions now. We can say f is increasing on, well, wherever there's positive signs here, so minus 1 to 0, union 1 to infinity. And how about where's f decreasing? That would be from minus infinity to minus 1, union 0 to 1. Also, we can talk about local max and min. Notice, for example, at minus 1 here, we go from decreasing to increasing, right? So that means at negative 1, comma negative 3, we're going to have a relative minimum or a local minimum. What about at 0 here? Well, we're going from increasing to decreasing. So that means right there, at 0, 0, we have a local max. And finally, at this last point here at 1, we go from decreasing to increasing. So at 1 comma negative 3, we also have a local min. And that completes that side of the chart, okay? Now let's do the other side. It's going to be basically the same thing. It'll be a little bit easier, just because this function is easier. I can pull out a 12 here, I guess. 3x squared minus 1. Let's solve that equal to 0. So 12 times 3x squared minus 1 is 0. That means 3x squared minus 1 is 0. So x squared is 1/3. So x is plus or minus the root of 1 over 3, which is the same thing as plus or minus 1 over root 3. And if we rationalize that by multiplying top and bottom by root 3, we get plus or minus root 3 over 3. What would the y values be for those? Well, when When x is root 3 over 3, the y value is going to be what? And when x is minus root 3 over 3, the y value is going to be what? Let me think. Well, let's just put that in the calculator. So I'm just going to type this in myself and see what I get here. So it's minus 5 over 3. And this one's going to be the same, right? Our function is actually an even function, so it's going to be symmetric about the y-axis. These are our potential inflection points here, right? Let's make a little chart now, just like we did before. We got minus root 3 over 3. We got root 3 over 3. And our second derivative is right here. If we think about it, any number here, if I put that in the second derivative, it'll be positive. Any number in here, such as 0, I put it in here, I'll get a negative. And any number, large number up here, I'm going to get a positive. So you know, back on over here, the plus and minus meant increasing and decreasing, because that was for the first derivative, right? But over here, the plus and minus are actually indicating concave up and concave down, because this chart is for the second derivative. So we can say f is concave up on, well, wherever there's a plus sign, right? So minus infinity to minus root 3 over 3 union root 3 over 3 to infinity. What about concave down? Well, from minus root 3 over 3 to root 3 over 3. And notice at both of these points, there is a change in concavity. It goes from plus to minus, and here it goes from minus to plus. So these points are definitely inflection points. So root 3 over 3, comma 5 over 3. And the other one, minus root 3 over 3, comma 5 over 3, are the inflection points. And now we actually have enough information to draw the graph. So let's start. Maybe I'll get a new sheet here. So we have to kind of summarize all this information, right? Why don't we start with our intercepts here? So our intercepts were at 0, 0 and root 2, right? And minus root 2. So this is 0, 0. Why don't we say root 2 is right here? And then minus root 2 would be here. So we definitely know the graph goes through these 3 dots. What else do we know? Let's look at our local maxes and mins. -1, -3. That's an important point for us. -1 would be somewhere around here maybe. -1, -2, -3. That's going to be a local min. And remember, we also have a min here at 1, 3. So this is 1. And sometimes I like to just make a little thing like this to indicate that it's like a low point. I'll draw it in better later. So it bottoms out here, right? And remember at 0, 0, we actually have a local max, right? So the graph is starting to take shape there. And I think we know what it looks like now, right? It goes down like this. Like this. Kind of messy, sorry. And then it goes back up like that. goes down. And there we go. It's a little bit messy over here. Something like that, right? So this is -1, -3. This is 1, 3. 1, -3. This is 0, 0. Let's get rid of this little piece here. And notice we have actually the inflection points are right here, right? It's a little bit hard to see, but it's like here it's concave down, but then it changes to concave up, right? And that occurs somewhere around, well, let's look what we have here. It's at 5/3, right? Which is 1 2/3. So it's about 1.6 or so. 1.666. Root 2 is 1.4, right? So sorry. Let me. Root 3/3 is actually what I should be looking at right now. Root 3 divided by 3 is 0.57. So 0.57, yeah, it's going to be somewhere around here, right? And 5/3 is around here somewhere. So the inflection points are right around here. This is 5/3. And this is root 3/3. And minus root 3/3. And those are the two inflection points. So we have our two local mins. They're actually even absolute mins. We have a local max, and here are two inflection points. And we have our x-intercepts and our y-intercepts all listed. So there's the graph of that.